So we're starting with 17.3, and this is on page 634 of your book. Formed elements. So, when we talk about development of the formed elements, we are talking about hemopoiesis or hematopoiesis, so you can use either term you want to. And this does occur in the red bone marrow, which is found in what organs? And maybe you find it kind of funny I'm asking you what organs?
Yeah, sometimes blood or bone. I mean.
Bones, right? Bones are organs. So basically any tissues that come together for a common function, they're called an organ. Of course, they're formed in bones. The hemocytoblasts come from hematopoietic stem cells. And these hematopoietic stem cells are relatively generic, although they can only develop into certain cell lines, so they can't develop into any cell lines. And these produce two types of stem cells. The lymphoid stem cells that produce lymphocytes, which are a type of white blood cell. And we discussed this in the laboratory. And then the myeloid stem cells that produce red blood cells and the other white blood cells as well. But the lymphoid stem cells specifically produce the lymphocytes. And the lymphocytes are the T cells and the B cells. Okay? We'll come back to those. So let's start with the lymphoid stem cells and the lymphocytes. They are involved in immune response, and they originate in red bone marrow. They stay the same. Some of the others migrate to the lymphoid tissues, like the thymus and the spleen and the lymph nodes. And then the myeloid stem cells give rise to all the other formed elements, as we stated before on the previous slide. And the ones that go to the thymus, by the way, are going to be the ones that become T cells. It's one of the reasons why we call them T cells. So, here's the development of the lymphoid stem cells. They become lymphoblasts, then develop into prolymphocytes, and then to a full lymphocyte. And different chemical stimulating factors are involved all along the way. Colony stimulating factors. These are hormones released by activated lymphocytes and other cells during the immune response, and their purpose is to stimulate blood cell formation. So this is one of the hormones that we didn't talk about in the endocrine system, and you're going to see this throughout the rest of the chapter. We didn't cover every possible hormone in that first chapter of the semester. The myeloid stem cells will become immature blast cells. The myeloid stem cells will differentiate into three types of progenitor cells, and then they differentiate further into either monoblasts and myeloblasts, megakaryocytes, or proerythroblasts. And the myeloid stem cells will become monoblasts and then turn into monocytes. And the monoblasts first differentiate into promonocytes, and then the promonocytes differentiate into monocytes. Okay, we also have some myeloblasts, or myeloid stem cells that become myeloblasts that turn into other white blood cells. The myeloblasts will differentiate in three types of myelocytes, which differentiate into what we call band cells. And those band cells will become three types of white blood cells: the neutrophils, the eosinophils, and the basophils. Okay, some of the myeloid stem cells will become megakaryocytes, which will then turn to platelets. So the myeloid stem cells will differentiate into megakaryocytes, which are really large cells that have large nuclei. One reason why we call them megakaryocytes. They will eventually shed their cytoplasm into these small membrane enclosed packets we call platelets. They're very small. When you were looking at the slides in lab the other day, you might have seen these little bitty pieces in between the other cells. And they're really just little flattening discs. Generally, you have 150,000 to 500,000 per microliter. And as you very well know, one of their purposes is to clump together. They stick to damaged vessel walls. They release chemicals that stimulate blood clotting. They are continually replaced. Each platelet circulates for 9 to 12 days. And they are eventually removed by phagocytes. And most of that occurs in the spleen. Okay, some of the myeloid stem cells will become proerythroblasts, which will then turn into red blood cells, or erythrocytes. So the myeloid stem cells can differentiate into proerythroblasts, that differentiate into erythroblasts, and then they shed their nuclei. Up to that point, they do have a nucleus. And then they become an anucleate reticulocyte, which then differentiate into what we know as our red blood cell or erythrocyte. And the stimulation of these progenitor cells to become red blood cells is stimulated by erythropoietin, which we have mentioned before, one of the hormones. It comes from the kidneys. So erythropoietin is released into plasma in response to low tissue oxygen levels, which we call hypoxia. And you remember last time I was saying that a lot of marathon runners go up to higher altitudes to train a few weeks before big races. And the purpose is to increase their red blood cell count because there is lower oxygen or partial pressure of oxygen at the higher altitudes, which will cause your body to produce more erythropoietin naturally. So the things that stimulate the EPO are anemia, so low red blood cell count. Reduced blood flow to the kidneys will do it. Oxygen content in lungs decreasing, and that may be related to disease or high altitude. Also lung damage. Stimulates the stem cells and the developing red blood cells in the red bone marrow. So this is an overall diagram of those cell lines, and this is a good diagram to get to know. So as you can see, in the very end, we have lymphocytes, monocytes, neutrophils, eosinophils, basophils, platelets, and red blood cells. And we'll talk about each of those in a little bit more detail. Okay, you've probably heard of hematology before, and certainly in hospitals there are quite often departments that are considered hematology. It depends where you work. I mean, some hospitals that are smaller may not have those individual departments separated out. Some do. And here we can tell a lot about a person's health by looking at the blood. You can detect different disorders like anemia, infection, clotting disorders. And when we talk about blood disorders, we use a term called dyscrasias. Whenever you have blood disorders, it can have systemic effects. So many different reasons for performing blood tests in addition to looking for disorders. You may want to determine blood type, which is what we did in lab last week. We can evaluate the types and numbers of red blood cells, white blood cells, and platelets, like in differentials. Any abnormal values can indicate certain problems, certain medical conditions. A complete blood count, or CBC, looks for all of these different readings within a cubic millimeter or microliter of blood. So we look for red blood cell count, white blood cell, erythrocyte indices like hemoglobin, the hematocrit, and other types of readings. And you see some of the normal ranges found over here on the right. And quite often we'll do a white blood cell differential count that identifies numbers of each of the type of white blood cells that tell us a lot about whether you have certain infections or certain disorders as well. And we'll get into that. Okay, as far as red blood cell tests, there's many types. We may just assess the number, but we may also want to look at the size and shape of some of the cells. That makes a lot of difference in determining certain disorders. And the maturity of the circulating red blood cells, how old some of them are. That may tell us something about, how well other organs are working, like spleen, in removing older cells. So we can detect problems that lack certain obvious signs, like internal bleeding. So in this table, it shows some of the types of tests you may perform, and it tells you what certain elevated or depressed levels may indicate. Let's look more detail about the red blood cell. So about 1/3 of all the cells in your body are red blood cells. That's a lot. All the cells in your body, 1/3 of them. A single drop of whole blood has 260 million red blood cells. Average adult, about 25 trillion red blood cells. And the average adult male has 4.5 to 6.3 million red blood cells per microliter. And a microliter is a little bitty amount. We actually have micropipettes in the lab that dispense these amounts. And a microliter, you can barely see the drop that comes out. You can see it, but just barely. So 4.5 to 6.3 million per microliter for adult males. For females, 4.2 to 5.5 million. And there's what your general shape looks like. It is biconcave. Again, no nucleus. When we look at stained blood smears, that's about all we see, as in this diagram. They have a large surface area to volume ratio, and they're packed with hemoglobin, which is a protein that carries the oxygen. This allows for a lot of oxygen exchange. The total red blood cell surface area in adults is about 2,000 times the total surface area of your body. And that tells you a lot about the importance of the red blood cell as well. They form stacks of rouleaux that help facilitate transport in your smaller vessels. The cells are very flexible. They can move through very narrow capillaries with diameters that are actually smaller than the red blood cell. How many of you have ever seen one of these videos or documentaries on TV of like an octopus squeezing through a little bitty hole? Well, it's kind of like that. They lose most of their organelles during development. Again, the mature red blood cells do not have nuclei, and we call them anucleate. They also lack ribosomes, so they cannot divide or repair themselves. But what's the importance of ribosomes in a normal cell? What do you recall? So ribosomes bind messenger RNA. For what purpose?
Producing proteins.
Yeah, to make proteins. And those proteins are what turns into structural components or enzymes or other things that a cell might need. Obviously, it cannot reproduce more of itself or repair itself if you can't produce those structural components. Lifespan of a red blood cell is less than 120 days. It's a very short time. So primary function of the red blood cell is to transport respiratory gases. Most of the red blood cell intracellular proteins are hemoglobin molecules, so 95%. The hemoglobin content of whole blood, 14 to 18 grams per deciliter of males and 12 to 16 in females. It has a complex quaternary structure, three-dimensional structure. It has 2 alpha chains, 2 beta chains, and it's similar to another molecule that we call myoglobin that you find in muscle cells. And a giveaway for anything that may be found in muscle, by the way, is that prefix there, MYO. Each chain has a single heme molecule, and that's what's shown here in this diagram. Each heme has an iron ion that interacts with the oxygen molecule. And when it does bind, we call it oxyhemoglobin, or we write it out as HbO2. When that happens, your blood becomes bright red. Oxygen binding is reversible. When it loses oxygen, we say it's deoxyhemoglobin, and then it is dark red. And by the way, is blood ever actually blue? It's not. The reason why we think it looks blue sometimes is because we're looking through the skin, and also because most of the time the blood that we're looking at, what we can see in our vessels on our arms or legs are veins. And veins carry the oxygenated blood, and that's darker blood, so it looks blue. Your arteries are usually deeper. And you'll learn that in one of the next chapters. Okay, a red blood cell has about 280 million hemoglobin molecules. Each hemoglobin molecule has 4 heme units, as we've already stated. So each red blood cell can carry greater than 1 billion oxygen molecules. About 98.5% of oxygen in the blood is bound to a hemoglobin. The rest is actually simply dissolved in your plasma. So some of the oxygen is carried simply by being dissolved. About 1% of the circulating red blood cells are replaced each day. Again, they have a very short lifespan. How many days did we say? 120. It's about 3 million new red blood cells that enter the circulation each second. Now, at the end of the life of a red blood cell, the plasma membrane ruptures. We call it hemolysis. Or the red blood cell is engulfed by a macrophage in the spleen, the liver, or the bone marrow, and then broken down. Okay, erythropoiesis is specifically red blood cell formation. What was the term we used for just blood cell formation?
Somewhat like that.
What was it? It sounded very similar to that. Anybody remember? It was either hemopoiesis or hematopoiesis. Okay, but specifically red blood cell formation, erythropoiesis. So this occurs in red bone marrow or the myeloid tissue and happens mostly in the vertebrae, the ribs, the sternum, the skull, the scapulae, the pelvis, and the ends of the long bones. What's unique about most of those bones mentioned there, other than the ends of the limb bones?
They're all irregular.
Yeah, they're irregular or flattened, right? Okay, fatty yellow bone marrow can convert to red bone marrow, by the way, in the case of severe or sustained blood loss, and make red blood cells if we need. Some good backup. So erythroblasts begin producing hemoglobin. Normoblasts lose their nuclei and become reticulocytes. And then the reticulocytes have about 80% of the hemoglobin of the mature red blood cell. And they enter the bloodstream after about 2 days. Now, macrophages are monitoring the condition of your circulating red blood cells. They engulf the old red blood cells before they rupture or hemolyze, and they remove the hemoglobin molecule, cell fragments. The heme units will be stripped of the iron, and then the iron is stored in the phagocyte, or it goes into the blood and binds to transferrin, which is a plasma protein. Then we convert the heme to biliverdin, then bilirubin. It goes into the bloodstream and then to the liver. So we're able to reuse a lot of this material. Your system's pretty good at recycling some of these parts. And then the globular proteins are disassembled and the amino acids are recycled. So macrophages have a lot of purposes, and once we get into the lymphatic system, you're going to learn that macrophages are the starting point for a lot of your immune processes as well. But you may have not known this fact. Any hemoglobin that's not phagocytized breaks down into the protein change, and that is excreted in the urine. If you have a lot of red blood cells being broken down kind of abnormally, you end up with a red or brown colored urine, and that's called hemoglobinuria. Okay, within the liver, bilirubin is excreted in the bile, and the blocked bile ducts, or if you have inability to process bilirubin, bilirubin levels will increase. It diffuses into your peripheral tissues, and this is what causes a yellow color in skin and eyes, or jaundice. And you see this in people that may have some cirrhosis or hepatitis because of that very situation. And again, keep in mind, bilirubin is kind of a normal component that we're hoping to reuse hemoglobin eventually from. But it doesn't always work exactly right. If we have blocked bile ducts, or we can't process the bilirubin, bacteria will convert bilirubin to urobilins and stercobilins, and then they enter the feces, giving it a yellow, brown, or brown color. So again, a lot of the colors you see in waste are because initially of the bilirubin and the breakdown of those bilirubins into other chemicals. Okay, in your kidneys, we excrete hemoglobin and urobilins, and this gives urine a yellow color. If you have intact red blood cells, though, in urine, this is hematuria. Generally, this isn't going to occur unless you have some kind of urinary tract damage. So hopefully you don't see that. This diagram summarizes all of those parts. Okay, now let's talk about something we did in lab the other day, which was blood typing. And what it enables us to be able to blood type, well, it has to do with certain molecules that are on your blood cells, and these are called antigens, as you recall. But in general, an antigen in your system is any substance that elicits an immune response. But even your own cells have an antigen. But hopefully your own cells' antigens are not seen as a foreign thing. Hopefully your body does not react to your own antigens and cause an immune response. So these should be recognized as normal or self, and you shouldn't react to them. So your blood type is determined genetically by what antigen is on the red blood cell plasma membrane. And we only talk about A, B, and Rh factor, or D, but there actually are more than 50 blood cell surface antigens. But these are the ones that make or have the most importance when we're talking about getting some kind of transfusion. So A, B, and Rh factor. So ABO blood group is based on whether you have the A or the B surface antigen. Another name for these particular antigens are agglutinogens. Now, plasma has antibodies in it that will attack foreign surface antigens, just in general. That's the way your system works, the way your immune system works. If your body has, or your system has not come into contact with something before, you will react against it. So you have 4 ABO blood types, or people in general. You don't have them personally, hopefully not. But you can either be A, or B, or AB, or O. So if you're type A, that means you do have the surface antigen A. If you're B, you have surface antigen B. If you have AB, that means you don't have A or B antigens. And if you're O, you do not have A or B antigens. Now, you remember in lab we kind of went over this also about, well, if that's true, then what antibodies do you form? So if you have an A antigen, your body's going to recognize A as itself. So are you going to form antibodies against A? No. And if you have B antigen, are you going to form B antibodies? No. Now, if you're the type O person and you don't have any antigens on your cell, are you going to form antibodies against A and B? Yes, because they're foreign to you. And what happens with these antibodies quite often is they will bind to those foreign things and make them clump together. So agglutination is the clumping together of red blood cells, and it occurs when the surface antigens, or the agglutinogens, are exposed to an antibody or agglutinin that reacts to it from another blood type. So this shows you, here we have red blood cells with surface antigen B, and here we have anti-B antibodies. That means they're antibodies that react against the B antigen. Notice they bind together. It causes those cells to bind together and agglutinate or clump, and eventually they will be hemolyzed and broken apart and destroyed. So you have cross reactions. And when you have these cross reactions, they can be dangerous because they can block some of the smaller blood vessels. They can cut the blood supply and damage and destroy tissues. And the cells may undergo hemolysis. Okay, the RH blood group is based on the presence or absence of the RH surface antigen. Now on your cards, in that third box when we did this on the Eldon cards, it had the letter D written on it instead of RH. Same thing. And RH actually stands for rhesus. Rhesus monkeys, where we originally found it. If you're RH positive, that means you have the RH surface antigen. If you're RH negative, that means you don't have the RH surface antigen. And this confuses people a lot. If we say you're A positive, I think, well, no, I know this is true, especially with some of my online students, you'll see this confusion. They think if they're A agglutinates, that they're automatically A positive, because that kind of makes sense to them that, well, they're positive for A. And that's not the way it works. If you're positive for A, that just means you're A. Because the positive negative part after the letters is the RH part. So you can be AB negative, right? Your A well or box can agglutinate. Your B box can agglutinate, and you can have no RH factor. That is AB negative. Okay, here's a general breakdown of people in the United States by different races. So genetically, we have different percentages of blood types. And for the most part, as you can see on here, that we generally see the O type as being the greatest proportion, except in Japanese Americans, and also Australian Aborigine. Those are the exceptions. And Korean? Well, no, that one's still 32. Mm-hmm. That's okay. Okay, the way the tests work, you put a drop of the person's blood onto, in our case, when we did the Eldon cards, onto that little box that already had antibodies on it. And now on some tests, you just drop the blood and then you add in liquid form the antibodies to it. Either way, it's the same thing. So when you dropped your blood into that A box, it already had A antibodies on it. So if it clumped up, that meant you definitely have A antigen because the A antibodies reacted with it, right? And the same thing with B, etc. And why do we want to do typing? To avoid transfusion reactions. They have to be compatible.
So if they're not compatible, it could kill you.
With what?
If you're not compatible, like if you have to get a blood transfusion and it's the wrong one, it could kill you.
Absolutely. Yeah, if you get the wrong one, it's going to cause the blood to actually agglutinate automatically. It could just simply block certain vessels. It can cause hemolysis of blood cells so that they don't work at all. Oh yeah, it can be very, very dangerous. So this table or this chart shows you what clumping looks like under the different scenarios of the blood types. And one thing you probably noticed when we did this in class is everybody's cards didn't look exactly the same under clumping conditions. Sometimes everything just kind of clumped in the middle. Sometimes it actually separated out into little itty bitty clumps. So it wasn't always easy to make a call. But looking at this chart, let's look at what kind of blood you can receive. I know we've gone over it before, but it doesn't hurt to go over it again. So if you are A positive, what kind of blood can you receive? Well, you can receive A blood, no doubt. And because you have the RH factor, you can receive positive blood. But you can also receive negative blood because Rh negative means there's no antigen there. So you can receive positive or negative. So you've just got to simply look at the A factor here for the most part. Now, can you receive B blood if you're an A person? No, because you're going to form antibodies against B. And you couldn't receive AB because it has the B antigen in it. So you can receive A positive, O negative. If you're B positive, you can receive B positive, O positive, and O negative. If you're AB positive, you can receive everything because you have all those antigens already, which means you're not going to form antibodies against any of it. So you're happy as you can be, you're a universal recipient. However, if you're O negative like I am, the only kind of blood I can receive is what? O negative. But luckily there's quite a few people that have it, but I can give my blood to anybody. So I'm a universal donor.
It's the same with O positive. They really only let you get O positive blood.
If you're O positive.
Yeah.
Well, and that's because of the Rh factor now. Yeah. You have to take that into account now because you do have an Rh antigen. Okay, genetics. It is determined by the genes that you get from the mother or father. Exposure to foreign red blood cells are not needed to develop the antibodies. Your body already has them for the most part. But anti-Rh antibodies are not automatically present. So you don't have to be exposed to the A or B the first time to react against it a second time. You will react immediately the first time. Rh factor, you wouldn't react the first time, but the second time you would. So an Rh negative person will not have any anti-Rh antibodies until they're exposed to an Rh positive and sensitized. Then they develop anti-Rh antibodies. And that's the issue with having an infant that happens to be, say, Rh positive and you're Rh negative. Or you're Rh positive and the infant's Rh negative. Usually the first child's not a problem, it's the second child. Okay. Blood types determined by combining genes from both parents, and I showed you some of this in lab with Punnett squares. Child can have a blood type different from either parent, right? During pregnancy, the mother's antibodies may cross the placenta and attack and destroy the fetal red blood cells. So that is what I was talking about as a problem, and that is hemolytic disease of the newborn. There's many forms. Some are very dangerous. Others are undetectable. Most common is when you have an Rh negative mother who carries an Rh positive fetus. At the first pregnancy, we rarely have a problem here because the fetal cells are isolated from the maternal blood and the mom's immune system is not stimulated to produce the antibodies to the Rh factor that first time. But at birth, you have bleeding at the placenta and uterus, and it mixes the fetal and maternal blood. Now the mother is exposed to the Rh antigen. This stimulates the immune system to produce the antibodies to the Rh factor. So this is sensitization. 20% of the Rh negative mothers who carry Rh children, Rh positive children, are sensitized within 6 months of delivery. But again, the first child is usually not affected because the antibodies develop after delivery. Subsequent pregnancy with an Rh positive fetus, the maternal anti-Rh antibodies can cross the placenta now and destroy the fetal red blood cells. And that would cause anemia in the fetus. The fetal demand for the red blood cells increases. The erythroblasts enter the bloodstream before maturity. That leads to erythroblastosis fetalis. And we have a high fatality rate if it's not treated. If we have a newborn with severe HDN, it's anemic and jaundice. because of the high bilirubin. The maternal antibodies can remain active for 1 to 2 months after delivery, and so we may require replacement of the infant's entire blood volume, believe it or not. So HDN can be prevented, though, by giving the mother anti-RH antibodies, called RhoGAM, at the 26th through the 28th weeks of pregnancy and during and after delivery. And what it does, the antibodies destroy the fetal red blood cells that cross the placenta before they stimulate the mother's immune response. And then she won't be sensitized. And that's shown here in the diagram. Okay, I'm going to show you the second video by the Crash Course A&P on the blood cells, and this one gets into the different white blood cell types. So this will be a good review or summary for this upcoming part of the chapter.